Today we're finding real roots. Real roots. That means only where your graph crosses the x-axis. Wherever it crosses, that's what we're looking for. In order to do that, we're going to factor, and in order to factor, our equation must be set equal to 0. If it doesn't equal 0, you have to rearrange it. So it looks like in example 1a, our equation does in fact equal 0. We'll get to that graph, that's so we can check our answer at the end. But we're just going to start off by factoring this thing. We're just trying to figure out where it crosses. According to this graph, it looks like it crosses here, and then it's a little hazy in the middle there where it crosses. So we're going to go ahead and factor. Number 1 rule, look for a GCF. What can we divide all those by? Looks like 3 and x to the third. So that's why we practiced factoring yesterday, so we'd be all ready for this. So it's 3x to the third out front. We write the leftovers next to it. The 3's cancel out, and x to the fifth divided by x to the third, 5 minus 3, is x to the second. Next, 18 divided by 3 is 6. And x to the fourth divided by x to the third, whoops, that should be a 3, is x to the first. And last, 27 divided by 3 is 9, and those x's cancel out. So we're going to keep going, keep factoring, because this is a trinomial. There's 2 factors left. So we have factors of 9 that add up to 6. Well, I'm pretty sure that's positive 3 and positive 3. So now we're going to keep going. Those are the factors. We're going to keep going whenever it says solve. That means actually write down what x equals. So we have 3 factors. You can put the one in front in parentheses if you want to. But we're going to set them each equal to 0. And solve. So when we solve the first one, we'll divide by 3. 0 divided by 3 is 0. And when we cube root to get rid of that 3, the cube root of 0 is 0. So basically, if you really want to skip all of this right here, what does x have to be for that whole thing to be 0? It has to be 0. So there's one answer. Next, we have x equals negative 3, and we have x equals negative 3. So it means the graph went through the x-axis at negative 3 right there, and through 0 right there. Alright, let's make sure this thing is set equal to 0. It's not, so we need to move the 36 over to the other side. So we're going to be factoring x to the fourth minus 13x squared plus 36. Now it equals 0. So we're going to need 4 answers here. But the cool thing about this is you can divide the x to the fourth into 2 sets of parentheses because x squared times x squared is x to the fourth. And see how this is an x squared? That makes us good to go. So we're going to look for the factors of 36 that add up to negative 13, just like we normally do. Factors of 36. Well, it's not 1 and 36. It's probably not 2 and 18. 3 and 12. Nope. 4 and 9. If we add those up, can we get negative 13? Yeah. If we do negative 4 minus 9, that'll be negative 13. So now we have those 2 factors. But I know there's 4. So I'm going to keep going. I do notice that these are special ones. These are perfect squares. And I know there's 2 factors left inside it. So for the first set, x times x is x squared. And what times what equals 4 and gives you nothing in the middle when you subtract it? plus 2, and negative 2. Same type of deal over here. There's 2 factors left over here. X times x is x squared, and we need factors of 9 that subtract to give us nothing in the middle. Positive 3 and negative 3 will do that. So now we just have to go through, set them all equal to 0, in other words, flip all the signs. So negative 2 is a 0, positive 2 is a 0, negative 3 is a 0, and so is positive 3. So if you were to graph this or look on a calculator, you'd see a graph that goes through negative 3, negative 2, 2, and 3. So it would kind of be some sort of a W that looked like that. Next, we'll talk about multiplicity. It just is how many times you have the same factor. So did anybody think it was weird how up here we have 2 of the same number? 2 of the answers were both negative 3, and I didn't even mention anything about it. I just left it. And we had that 0, but really 3 of the answers were 0. That way, when you have x equals 0, x equals 0, and x equals 0, we have 1, 2, 3, 4, 5 answers, and that exponent's a 5. Over here, the multiplicity of these roots, they were all 4 different ones. So those each had multiplicity 1. But over here, we would say that the 0 had multiplicity 3. So you'd write multiplicity 3. And the negative 3, since there were 2 of those, you'd say that those 2 had multiplicity 2, because there were 2 of them. So that's what we're going to do from now on. The other cool thing is, depending on if it's an even or odd multiplicity, it'll show you what it looks like on the graph. It'll either touch the x-axis, just come up and touch it and not cross it, or it will bend and then cross it, depending on if it's even or odd. If you have an even multiplicity, such as a multiplicity of 2, like number 1, this is the graph for number 1 up there. Remember how we had negative 3 twice? An even multiplicity just bent. It did not cross the x-axis. But when we had the 0, there were 3 of them, because it was x to the 3rd. 3 is an odd multiplicity, and so it bent there, and then it kept going across the x-axis. So we're going to do the same thing with the next problems, but we're just going to state the multiplicity when we're done. So we have it set equal to 0, and we need to look for a GCF. I'm thinking 2 and x to the 4th. So we'll divide everything by x to the 4th, 2x to the 4th. So we write the GCF out front and start canceling out. Those 2's cancel. 6 minus 4 is x to the 2nd. Negative 10 divided by 2 is negative 5. 5 minus 4 is just x to the 1st. And negative 12 divided by 2 is negative 6. Those x to the 4ths cancel out. So I recopy the 2x to the 4th. I put my 2 sets of parentheses so I can factor this trinomial. I'm looking for factors of 6 that subtract to get negative 5. So I need an x and an x. And how about negative 6 plus 1? Negative 6 times 1 is negative 6, and negative 6 plus 1 is negative 5. So I need to keep going and solve. See how this x is out front, and it has that 4 right there? It means that we're going to have 4 of them. 4x equals 0s, because the only number that works right here so that that equals 0 is 0. So you can write down 1x equals 0, but then we're going to write underneath it multiplicity 4. Okay, so that'll save you the trouble of writing x equals 0 4 times. Next, we're going to write the next answer. It was minus 6, so our answer is positive 6, and that was the only one. So we're going to write multiplicity 1. Last, we have x plus 1, so the 0 will go through negative 1, and we only had one of them. So you need to write that the multiplicity of that is 1. So this is the final answer. It means we have 1, 2, 3, 4, 5, 6 different zeros to account for that exponent being a 6 up there. If you graphed it and looked at the graph, since the 0 has a multiplicity 4 and 4 is even, it would look like this type of a situation on 0. Try 2B and see if we come up with the same answer. The first thing I did to give you a hint is I moved the 50 over, so everything was on one side. And now since I have 1, 2, 3, 4 terms, I'm going to unbox it. So I have my 4 boxes and I filled them in, and now I'm going to look for GCFs. Now that I've unboxed it, I'm just going to double check real quick it all makes sense. X squared times x is x to the third. X squared times negative 2 is negative 2x squared. Negative 25 times x is negative 25x. And negative 25 times negative 2 is positive 50. So I did factor it right. I'm going to write them in parentheses. X squared minus 25 and x minus 2. So which one can I keep factoring? I can keep factoring that one because it's a perfect square. I can find factors of x, or factors of 25 that subtract to get 0. It'll be a plus 5 and a minus 5. So here are the 3 factors, and there's a 3 up there, and it turns out these are all different. Negative 5 is an answer, positive 5 is an answer, and positive 2 is an answer. Since there's only one of each of those, to save you space, if you want to put a little bracket around all of them, you can put that they all have multiplicity 1. Factoring doesn't always get us all the answers that we need, so we have this thing called the rational root theorem, just in case factoring or unboxing doesn't work out. And what we do is, if we have a polynomial with integer coefficients, which means all the numbers are not decimals, then all the roots, all the answers, can be written in the form p over q, where p is a factor of the constant term, the last term, and q is a factor of the leading coefficient, the first term. So we can use the possibilities. We come up with a list of possibilities, and then we start dividing by them until we can factor. If you don't want to use a list and trial and error to narrow down where a root is, you can just look on a calculator and then keep going that way. So we have to use it because, honestly, the box method, unboxing and grouping, doesn't always work. So I'm actually going to skip 3a, just because it's kind of a bad problem, and we're going to jump right to 3b. So the constant term is p, the leading coefficient is q, and so the factors of 8 are going to go on the top. So 1, 2, 4, and 8. Those are all the factors of 8. And the factors of 1 are going to go on the bottom. And the only factor of 1 is 1. So when we divide the top by the bottom, 1 divided by 1 is 1. 2 divided by 1 is 2. We only have 4 possibilities here. Since they are factors and we don't know if we are multiplying positives or negatives, we also have plus or minus signs in front of all of them. So we actually have 8 possibilities. So what we do is we start using synthetic substitution, and we just try them until we get 0 for a remainder. So let's get our coefficients. Make sure, let's test 1 first, just to start at the beginning. And we're going to write down our coefficients. We have x to the third, x to the second, x to the first, and no x's. And the coefficients are 1, 3, -6, and -8. So we'll drop the 1. 1 times 1 is 1. 3 plus 1 is 4. 1 times 4 is 4. -6 plus 4 is -2. 1 times -2 is -2. And -8 minus 2 is -10. So since we did not get 0 for a remainder, it means that 1 does not go into that evenly. It means the factor x minus 1 doesn't go into that evenly. So it's not positive 1, so we can check that off the list. Let's try positive 2. So same thing again, we're just going to put a 2 in the box, and we'll write down the coefficients again, just like we did, the 1, 3, -6, and -8. Drop the 1. 2 times 1 is 2. 3 plus 2 is 5. 2 times 5 is 10. -6 plus 10 is 4. 2 times 4 is 8. And -8 plus 8 is 0. So since we got 0 for a remainder, it means that x equals 2 is one of the answers. Well, if x equals 2 is one of the answers, one of the roots, it means that x minus 2 must be one of the factors. So what we can do, now that we have x minus 2 as one of the factors, is we can take the leftovers. So remember, when you do synthetic, you knock down your exponent by 1. So we started with x to the third. So our leftovers down here, we're going to start with 1x to the second, and then 5x, and then 4. And our remainder was 0. So we need to factor that. So the two factors are, what are the factors of 4 that add up to 5? Plus 4 and plus 1. So those are two factors, and the x minus 2 is also a factor, and we really should write it out front, although I don't have space, so I'll write it next to it. So those are the three factors, which means we can get the 3 zeros, -4, -1, and positive 2. They each have multiplicity 1, and those are the 3 real zeros. By the way, just in case you didn't believe me that the box method, unboxing your grouping, doesn't always work, let me just verify that with you up here by trying to unbox that problem. So let's do that, just so you believe me. If I put x to the third, 3x squared, -6x, and -8, and I go through and pull out the GCFs, x and 1. When I go to check it, it doesn't work out. Okay, I just did that really quickly, and I realized that this should be an x to the second. So x to the second times x is x to the third. X to the second times 1 is not 3x squared, but that's the biggest GCF over here. -2 times x is not -6x. And -2 times 1 is not -8. So see, the box didn't work, unfortunately. That's why we have the rational root theorem, or a calculator.